Alright guys, let's do this problem that says the stiff leg derrick used on ships is supported by a ball and socket joint at D and two cables BA and BC. The cables are attached to a smooth collar ring at B, which allows rotation of the derrick about the C axis. If the derrick supports a crate having a mass of 200 kilograms, determine the tension of the cables at X, Y, and C components at the reaction at D. So first let's draw the free body diagram. We know we have a tension here. I'm gonna call this tension A, and you know you have a tension here, and I'm gonna call this tension C because it's going towards point A and C respectively. I'm gonna call this point right here, I'm gonna call it point E just for reference. You know we have a weight right here. We know that the weight is equal to minus 200 kilograms times 9.81 because it's the acceleration of gravity, which is equal to, and this is on the K direction, which is equal to 1962 in the K. It won't let me draw the 2. Let me move the 2. Minus 1962 in the K. And then we also have the reactions at D. Let's call this dx. Let's call this dz. And let's call this dy. The first thing that you want to do is write down all the forces. So let's start writing the forces at D. And the forces at D are dx in the I plus dy in the j plus dc in the k. Then let's write the force of the weight, which is only negative 1962 newtons in the k. Then we have tension at A and then tension at C. Now we need to figure out tension at A and tension at C, and that's kind of simple. So tension at A is equal to a unit vector going from B to A times the magnitude of the tension at A. Now the unit vector is equal to a vector that goes from A to B over the magnitude of that vector, which is equal to, so sorry, that's not A to B, that's B to A. B to A. Now from B to A, you know that you are going 2 in the I, minus 3 in the J, minus 6 in the K. And you gotta divide it by the magnitude of that vector, which is 2 square plus 3 square plus 6 square, all that square rooted. So that would be 7, because 2 square plus 3 square plus 6 square is 49. Then the unit vector comes out to be 0.286 in the I, minus 0.429 in the J, minus 0.857 in the K. That means that this vector TA is equal to 0.286 TA in the I, minus 0.429 TA in the J, minus 0.857 TA in the K. And that we can write down here. 0.286 TA minus 0.429 TA in the J minus 0.857 TA in the K. Now we need to do the same thing for TC. I'm going to move a little faster on this one. Unit vector from B to C times the magnitude of TC. The unit vector from B to C is equal to the vector from B to C over the magnitude of that vector, which is equal to minus 6 in the I, minus 3 in the J, minus 6 in the K. And all of that over 6 square plus 3 square plus 6 square, which should be 81, and square rooted is 9. And that means that this vector comes out to be 0.667 in the I, minus 0.333 in the j, minus 0.667 in the k. And that means that the vector tc is the same univector times the magnitude tc minus 0.333 tc. This is in the I, this is in the j, minus 0.667 tc in the k. And then we'll just write it down here. 0.667 tc, this is in the I, minus 0.333 tc in the j, minus 0.667 tc in the k. And that's it, we got all our forces, and we know that when we add them all up, they should be equal to 0. They should together should cancel out. So that being said, we can come up with 3 equations. An equation for the x by adding everything that's on the I, which would be dx plus 0.286 dA minus 0.667 dc is equal to 0. In the y, we know that dy minus 0.429 dA minus 0.333 dc is equal to 0. And in the z-axis, we know that dc minus 1962, this is in newtons, minus 0.857 dA minus 0.667 dc is equal to 0. So perfect, we got 3 equations, but the problem is that we have 1, 2, 3, 4, 5 variables and only 3 equations. So obviously this is a problem. We're going to need another set of equations of another way of solving for some variables in order to be able to solve this system. So let's just save this equations and we're going to put them aside for later. And let's start a new page. So what do we do from here? Well, since if you remember our free body diagram, actually let me bring it back up. You know that at point D we have 3 variables, and at point B we have 2 variables. So usually what you want to do is pick a point and do the moments about that point. And which point should you pick? You should always pick the one with the most variables, and that makes the problem easier. So let's give this a shot. If I do sum of the moments about D is equal to 0, I'm saying that dB cross dA plus dB cross dC plus dE cross the weight is equal to 0. So basically what I'm saying is that I'm calculating the moment being created by each of these forces, which are dA and dC, and then the weight. Remember that the weight happens at the point which I am calling E. So I basically have to make these matrices and solve this system, and once I do that, then I should be able to get a couple of more equations or something that will help me solve for TA and TC. And since I'm doing the moments around about D, then I know that the reactions at D are going to be out of the picture. That means that whatever equations I get are only going to have TA and TC, because I already know the weight as well. So let's do this. Let's do dB cross TA first, and I'm going to try and cramp it up here. Hopefully you guys understand. So first you do the matrix IJK. Now the first row is IJK. The second row is from D to B, which is 0 in the I, 0 in the J, and positive 6 in the K. And then you got to do TA, which we got at 0.286 TA minus 0.429 TA and minus 0.857 TA. Should make the numbers a little bigger, apologies for that. IJ, repeat first and second columns, 0.286 TA minus 0.429 TA, and then we do our positive diagonals. So the first one's I times 0 is already 0, J times 6 times 0.286 is 1.716 TA in the J. The third one is K times 0, so it's 0, and then our negative diagonals, which is negative times 0.286 times 0, 0, negative times negative 0.429 times 6 times I should be, it's 2.574 TA in the I. This is a 2, I swear it's a 2, and then the last one has a 0, so it's also 0. So we have the first one. We just got to do the other two. So the second one is dB cross dC. Gonna go a little faster for this one. IJK, dB is 0.006. This is negative 0.667 dC. Second one is negative 0.333 dC, and last one is negative 0.667 dC. Repeat first and second columns, 0, 0, minus 0.667 dC, minus 0.333 dC. Positive diagonals. First one 0, second one is minus 4 dC on the J, third one 0. Negative diagonals is 0, the second one is plus 2 dC in the I, and the last one is 0. So we have the second matrix solved, and the last matrix is D cross W. IJK. You know that from 0 to E is slightly different. It's 1, 4, and 7.5. And then the weight is 0, 0, and it's going straight down at negative 1962. So repeat first and second column, 1, 4, 0, 0. So first one is minus 7848 in the I, then it's 0, then it's 0. Negative diagonals is 0, 0, and then positive 1962 in the J. And now what we got to do is we got to add the I's, the J's, and the K's, and we know that the sum of them should cancel out and equal to 0. So in the I, we know that 0 is equal to 2.574 TA from the first one, the I that we got in the first one, plus 2 TC minus 7848. So we could clean this up a little bit, and we get that 7848 is equal to 2.574 TA plus 2 TC. Let's call this equation 1. In the J, we have that 0 is equal to 1.716 TA minus 4 TC plus 1962. So let's clean this up a little bit. We get that 1962 negative is equal to 1.716 TA minus 4 TC. And what I'm going to do is I'm going to get this equation 1. I'm going to put it here, but before I put it here, I'm going to multiply it by 2. Once I do that, I'm going to get that this is equal to 156.96 is equal to 5.148 TA plus 4 TC. So if we sum these two equations, the TC cancels out, and we get that 13734 is equal to 6.864 TA. And we solve for TA, and this is equal to around 2000.9 newtons. So look, we found TA. So if we plug this TA back into equation 1, we should be able to solve for TC, and we should get that it is equal to 1348.9 newtons. So we already have TA and TC. And all we need to do now is we need to plug these two numbers into the first three equations that we found on step 1, which are these equations right here. And if you do, you should find that dx is equal to 327.45 newtons. dy is equal to 1307.55 newtons. And dc is equal to 4576.45 newtons. Final answer for the reactions at D, and final answer for the tension that goes towards point A and the tension that goes towards point C. If you made it this far, please make sure you go to finalanswer.com. There you're gonna find all the videos I've been working on and 6 ways to support this channel. And make sure you check my merch store by going to store.finalanswer.com.